This is a preview of lecture number 3 in the Einstein Mathematics High Performance Program for grades 6 and 7, roughly age group 11 to 13. So in this preview, we shall consider some items that may help you to solve some of the difficult problems that are part of the lecture. So let us commence with the preview of some of the questions that are going to appear. Now, we're going to start off with a very interesting item, and that's the map coloring problem. This is an amazing result that is well known in the world of mathematics, but a proper proof hasn't come forward yet. Whether it's true, we know by means of a computer. Using a very high performance computer in the olden days, a supercomputer they used to call it, this result was established. Now, what is the result? Well, take any map you know and try to color it in such a way that two countries that have the same boundary do not have the same color. Obviously, that makes sense. So if you take this country, if you take this map here on the side, we have to use different colors. So let's choose, say, red for that place, green, and blue. We can't use red or green again. So we will need 3 colors there for that map. 3 colors. Take a different one. Let's try this one. You could have red, green. I could have red again because red and they're not touching each other. Here I have to use a new one. I have to use a blue perhaps there, but I could use green again here so that I don't waste colors. The name of the game is to work out what is the least number of colors you need to color any map, no matter how complicated. And there's an amazing answer to that problem, which we will discover in the lectures. So let's carry on with this one. Green, red, I could use blue again there, and that's colored. So I was able to color that map with a total of 3 colors. Still, how about when the maps become much more complicated? Okay, can you make your own map and try it out? Let's make a map of our own of this type here. Lots of countries. But let's make it complicated. How many colors do you think you'll need now to color this map? Well, try this out and you'll find that the result is quite astounding. So let's try red, green, blue, red again, green, I could try blue there, right? And so on. Did I say red, green, blue, red? Oh, hang on, we can't use that red again because they are next to each other. So we're going to use a new color. Yeah, let's use a new color called, let's say, yellow. Okay, let's try a different color there so that we are safe. So now I'm ending up using another color. Okay, here we could go back to the old red. I can use blue there, yellow there, green there. How about this being what? Yellow, green, red, blue, red. Okay, and we carry on like that. And let's see how many colors you need. You will be quite shocked to learn that the total number of colors that you will need will not be more than a certain very small number. What do you think it could be? 3, 4? Well, we needed 4 there. 5, 6, 7? Well, why don't try this out yourself and check what the result could be. Now, this result was known for a long time, and people didn't know how to prove it. So until they could actually prove it, the result was known by the word conjecture. A conjecture is a very good guess based upon very strong evidence. But a proof in mathematics needs a logical set of statements that everybody can accept based on known knowledge. On the other hand, if you think it's wrong, you can then produce what we call a counterexample. Counterexample is one example where the problem doesn't work, and then it can have no hope of being proved. An example of a conjecture is the famous Box conjecture. In this conjecture, Box made the statement that the mathematician Goldbach said, any even number bigger than 2 can be written as a sum of 2 prime numbers. Do you remember what prime numbers are? Prime numbers. Prime numbers are numbers with only 2 factors, or 2 divisors. 2 factors or 2 divisors. 1 and itself. So, example, prime numbers are like 2, 3, 5, 7, 11, 13, and so on and so on. If you take any even number, you can always write it as a sum of 2 prime numbers. Try this out. Right? Let's take the first 20 numbers. Well, those ones are easy to see that if you take small numbers, that's easy enough. But let's take a number like, say, 20. Can you write it as a sum of 2 prime numbers? I can. 7 plus 13. Okay. Or we can choose 3 plus 17. So this one has got 2 ways of writing it. Take the number 50. Can you write it as a sum of 2 prime numbers? 31 plus 19. Any other ways of doing it? 17 and 33 won't work. If you take 23 and 27, no, they don't work. 27 is not prime. What else could we use there? 3 and 47. 3 and 47, that works. Is there any other way of doing this? 7 and 43. So sometimes you can do it in many different ways. But Goldbach conjectured that any even number bigger than 2 can be written as a sum of 2 primes. If you find one even number where it doesn't work, then you will have disproved Goldbach's conjecture. Now, under problem solving, we've got a few questions here to help you to reason a bit. Complete the magic square. Magic square, you know, means has the same magic sum or total, whether you go column wise, row wise, or diagonal wise. You must get the same magic answer. Now in this one, it's a 5 by 5 block. If you look closely, it's 5 by 5. And the numbers go from 1, 2, 3, all the way up to 25. Now, it's not so easy because what we have done here is that we have actually left off 2 numbers in most cases. So it makes it a bit hard for you. So there's a number missing there and there, something missing there and there. And on the diagonal, there's something missing there and there. So you've got to use some hunch to get started. And once you get started, you can then carry on by trial and error and see if you can make all the totals to be the same. But the first thing to figure out, guys, is what is the magic total? Well, if you add up 1 plus 2 plus 3 all the way up to 25, go back to lecture number 1 to see a quick way to do this. The answer will be 25 times 26 divided by 2. Then you take that answer and divide it by 5, because there are 5 in every column, every row, and every diagonal. So you take that answer divided by 5, and you'll get the magic total that you're supposed to be aiming for. So try that. Let's see how well you manage on that problem there. Secondly, 3 soccer teams played against each other in a tournament. The following table gives information about the results. So you got the 3 teams, aces, bucks, and chefs. Okay, so of course, if you got 3 teams, what are the possible games? You will have aces versus bucks, aces versus chefs, and lastly the chefs versus the bucks. You want to know what was the score in each game. Now each team played 2. Obviously, they could have either won 2, won 1, or lost 2 games, or there could have been a draw. They could have had drawn matches, okay? So then, can you work out? So according to this here, aces lost 2 games. Bucks, there's no information there, but chefs have drawn 1 game. So isn't it logical to say that chefs have got a draw against Bucks? Chefs versus, sorry, the Bucks versus chefs, yes, they must have had a draw. So what is the possibilities? The draw could be 0-0, could be a 1-1 draw, 2-2 draw, and so on. So if you look at the goals for, 2 were scored by aces, 3 were scored by Bucks, 2 were scored by chefs. So you can't go to too high numbers. The total number of goals for was 7. Obviously, the total number of goals against is also 7. Use that information. Let's see if you can come up with a score in each match. Then we move on to the final one, which is an alphametric. Alphametric is where letters stand for different digits, and they stand for the same digit each time they appear. So if you got the alphametric send more money, these are famous puzzles. They used to appear in newspapers, but they're actually intelligent mathematical problems. Send more money. Now the M stands for the same number all the time. I think you can easily see that the M has to be a 1. Isn't that so? So it'll be a 1 in both places. 1 plus something, S, must give you back this 1. See, because you carry over, you see? Something with a 1 that can carry over. Now, can you fill in the rest of the letters? What do you think they mean? Which numbers do they represent? Remember, if you choose something for E, it will be the same every time the E appears. So use your trial and error sense, and let's see how well you do with that problem. We'll meet in the lecture proper. See you guys then.